can be finished and I upload it to the YouTube channel. Also, prior, I tried to put it on a YouTube channel that's different, and I didn't have access to put a big file there or a long video. Now I can. This is that's just I find some reliable way to get it to. I did get some other suggestions from people of other ways for sharing, so thanks for that. Okay, regarding your project, it's still not online, but I hope it will be today or tomorrow. So that's project 1, but you certainly have a lot of things to do with the self-study guide so far, and you're ramping up towards that project. Regarding Piazza, so I only got around to it today to actually set up Piazza, where we have sections for project 1, for project 2, for the problem set, for the exam, and for the self-study. So feel free to engage with each other, with the tutors, and certainly with me in Piazza, and push me forward. Frankly, I've never used Piazza before, but once we get a few discussions going, we'll see how it goes. All right, let me just see anything else here in the chat. No. All right. Are there any questions about activity 1? So I'll move straight on to activity 2. We pretty much started activity 2 last week, but you would have spent a bit more time probably on activity 1 before going to activity 2. Are there any questions, or can I move on directly to fly through activity 2? No? Okay, so activity 2. So we're here dealing with class structure, and we're looking at the 2 in general. That's kind of what's happening in this activity. So it's all about decomposing the Markov chain into different classes and seeing when we hit certain states, with what probabilities we hit certain states, etc., etc. Often when we're modeling, the class structure will be kind of evident. There might be like one state which is maybe the absorbing of one type, and another is absorbing of a different type, like we had with Gambler's Ruin, or there might be kind of a total catastrophe state, as we have with the branching processes, extinction, and then all other states and things like that. Okay. But the associated probabilities of hitting times, we've already done some things like that in week 3 of semester with the Gambler's Ruin before we really spoke about Markov chain. Now we'll see it in a slightly more detailed manner. So I'm starting here. We're looking here at this is MC1, which I hope you would have read through already, or at least the first pass. So that's in activity 2. And basically, there is a very simple definition of a state I leading to state J, meaning that there is some probability of going from I to J for some n. Okay. In terms of our transition probabilities, what we get, that just means that Pijn, which is the ij's entry of the transition probability matrix raised to the power n, is greater than 0 for some n. So there exists some n greater than 0, greater or equal than 0, where this is true. Okay, so that means that you can go from a state I leading to J. Now, a state I communicates with J, and we use this kind of this double arrow thing, this guy. Yeah, you see it? Big on your screen, these 2 arrows. All right, so if I leads to J and J leads to I. Now, I put these exclamation marks as I was reading this just a bit before. Just to note, I mean, this by the way, is a typical standard definition of leading to and communicating. But keep in mind, and these subtleties are a bit important, when you move to the other text, SP1, okay, so this is, we're now looking at SP1. Where is it? So I'm here in the middle of section 1 of SP1. We'll get here soon. Okay, this is SP1. This is a Duret book, stochastic processes, essentially stochastic processes. Okay, in chapter 1. So he calls X communicates with Y, meaning that you can get from X to Y. Okay, so his communicates is the Norris's leading. Okay, so keep in mind that these means different things. Okay, that's the arrow X to Y, so it means that there's a probability of getting from X to Y. So slight differences there, just to keep that in mind. Okay, so this first theorem is quite straightforward. It just says that, you know, a state I leading to state J is equivalent. So when you have three statements and they're equivalent, it means that if I want to be able to show if one holds and two holds, and if two holds and three holds, and if three holds and one holds, and each one shows the other one, okay? Or I want to show that each one implies the other one and vice versa. So I leading to J means that there is some positive path going from I to J. That is this, and it means that Pij is greater than n for some n greater than 0. That's what I wrote here. Okay. Now the proof of this is quite straightforward, but just so you see, this book, the MC1 book, is slightly more mathematical. So basically, first of all, there's a statement here that Pijn is less than the probability of starting in state I and going to state J for some n. Okay, because this event here is a union of getting there in n1 or n2 or n3 or n4 or n5 or n, and this is for some specific n. Okay, so that's why this, let me erase all these scribbles, that's why this first inequality. Okay, now this second sum, which is no longer even a probability, would treat, if you would just add each of these probabilities, well, that's the sum of all of the probabilities. Okay, so that's the second sum, and that's why you have a second inequality. Right. So these two inequalities prove the equivalence of 1 and 3, because you can see if one holds, you want to say if one holds, so I leading to J, you want that this thing would be positive. That's how we defined it. Okay, well, if that's positive, then this thing is positive. So that means that Ij is greater than 0 for some n. So some element of this sum, this is the sum of non-negative terms. Probabilities are non-negative terms, is positive. And the other direction goes from this side. Okay. So that's the first step, and the second step just follows from the meaning of what Pijn is. Okay, so if this is not evident to you, then just go back and think about what we mean by a matrix product. Okay, so when we mean a matrix product, the ij entry of the matrix product, we're actually looking at the sum of all of the possible paths where we can go from state, and here, let me zoom in a bit, we can go from state I to state J. And there's all kinds of different paths that you can do in the way. Okay, I assume that's quite straightforward. So once you get to that, it's also easy to see that transitivity holds, that if I leads to J and J leads to K, then I leads to K. So that's kind of transitivity of this. And also a state leads to itself just by definition. So then if you actually take not the leading to, but the communicates with relation, so it's a relation for those of you that did Math 1061 or courses that follow on for that, right? The relation is some subset of the Cartesian product of the state space, and if not, then no big deal. This is just go around this, okay? So since these things since it satisfies a condition of an equivalence relation, that's not written in this book, but that means that it's symmetric and reflexive and transitive, then that actually means that this equivalence relation actually induces a partition on the state space. And that's what we spoke about the last time. So we have the state space here, and we're actually going to partition it into, it'll be this set and this set and this set, okay? The set 1, 2, 3, the set 4, and the set 5, 6. So all the elements in this set communicate with each other, because you can get from 1 to 3 and from 3 to 1 and vice versa. All of the elements in this set, that's this one, the singleton set, communicate with each other, because you can get from 4 to 4, okay? And all the elements in this set communicate with each other, okay, in this third set. So basically, the class structure induces a partition on the state space, okay? That's this third set, okay? That's this first one. Questions, thoughts about this? Now, how does one find it algorithmically? For those of you that, and it's not all of you that are kind of doing computer science algorithms course, one way is an algorithm in a directed graph for finding all of the connected components. Okay, you can use that. But on small Markov chains, you can just figure it out. All right. So if I go back here to activity 2, what you want to do, so we read the, I just can't annotate here on the web browser. So I can't write on this easily. I mean, I can, not easily, but I cannot easily. All right, and we read, or you'll be reading in greater detail or have read through MC1, and exercise 121 is pretty much doing this type of thing that you have in the example. Okay, did it once, moved on. All right, the next thing that you suggested to do is to have a rate of SP1, and SP1, well, do it twice even. That's what the study guide says, do it twice. Okay, and that's a long section. So let's get to SP1. And SP1 doesn't take a straightforward approach as the MC1 book, but rather speaks immediately about hitting probabilities and return times and things like that. Okay, so throughout in both books and almost everywhere, and we've used this before, you'll see the notation of putting a subscript here. Here, X is a state. We used I's and J's in the MC1 book, but we are here in the SP1 book. Okay, all right, and X is the state. So starting in some given state, what is the probability of some event A happening? Okay, A can be kind of any event. All right. Now, the events that we're often interested with have to do with random variables that are hitting times, or here they call it the first return time to Y. Okay, the first return time to Y. So it's the way they define it here, and you sometimes need to look at the subtleties. Sometimes it'll be the minimum n greater than 1, sometimes it's minimum n greater than 0. And it depends for in different contexts. And Lawrence is asking, does TY mean I have a particular change in mind? So TY depends on internal, or should I think of TY as the shortest possible Y? Okay, so Lawrence asks that TY have a particular chain in mind. Okay, so this is the answer. So given a Markov chain is a probability law, it describes a probability law of a collection of random variables. It's a random process. Okay, so that collection of random variables can have different trajectories. As you see the different trajectory, you can look at the trajectory and say, oh, for that trajectory, I will have that TY. Okay. Now, the way TY is written here, it doesn't say where you start here, at least in this line. We don't see where it starts. It simply says, what's the infimum n? Here, this book is trying to be a bit less formal, so they write minimum, but the thing is that that can be also infinity. Okay. What's the infimum n such that X of n such that the trajectory hits Y. Okay, and that's how you get T of Y. That's a random variable. If you see the trajectory, in essence, you can say what T of Y is. Okay? Now, T of Y can actually be infinity, and that's why you call it, you might say this is actually an event. This thing plays the role of A here. Okay, that's the probability of T of Y being finite. Okay. Now, when we define rho, did that help, Lawrence? Tell me if not. Okay. Okay, good. Thanks, Lawrence. All right, and then we define rho YY. That's the probability of starting in state Y and reaching state Y in finite time, so returning, okay? And that's why he called it the time of first return to Y. But this is actually bad to call this random variable the time of first return to Y because we didn't say here where we started, okay? So here it's just the time of hitting Y, and actually later in the section. So I think the author did a bad job with this. Okay, but you know the nice thing about the iPad, you can do all this in one undo. Whoop, bring it back, 2 undos. Yeah, all right. Time of first return. So later you'll see that there'll be probabilities of the form Px Ty less than infinity, and then it's no longer the time of first return to Y. It's the probability of hitting Y given that you started in X. Okay, so this is a probability of hitting Y given that you start in Y. This will be the probability of Y given that you start in X. And guess what? This is going to be called Pxy. Okay, that's a bit below. All right, so these are return probabilities. Okay, let me actually jump to the MC1 just so you see these in MC1. So I'm moving now to the next section in MC1, which in your reading is the next thing to read. Okay, so let's see how these things are defined in MC1, and it's pretty much the same. All right, so section 1.3. I'm looking now at section 1.3. So momentarily, I'm skipping this item, which is read SP1, this item which you have here now at the top of your screen. And I'm moving to the last item, which is read MC1, section 1.3. Okay, so reading these things together is pretty good. All right. I'd like to get some feedback in general. You don't have to do it now. You can send personal messages in Piazza, WhatsApp. No, you can't send me WhatsApp. No WhatsApps. You can send me in different ways of in general how you feel about this reading. So I'd like to know for who it's working, and you'll probably know by now or in a week or so, and for who it's not. My view is that we're kind of in much greater isolation, all of us in the society, but certainly the cohort of this course. And then, you know, if you got kind of given with texts, then you can actually spend time with these texts and read, and just have these meetings for a review. So I'd like to kind of hear from you guys in one way or another how it works, from you guys and from everybody how it works. All right. So section 1.3. Let X and be a Markov chain with transition probability matrix P. Fine. And here they define the hitting time of a subset A. Okay, so it's trying to be more general of I. What's I? What's I in this book? The identity matrix. What's I? Subset A of I. In this book, it's a state space. It's a state space. Okay, this book I is a state space. So I can be the states 1 to 7, or I can be the states happy, sad, very happy, etc., etc. Okay, that's a state space. So a subset of the state space. So here, let's see what they mean here. So HA, first of all, this is just a mathematical notation for writing a function, right? So HA is a function from this thing omega. That's the domain, and that's the range. All right. So omega are points in the sample space. Okay, and we don't speak about it much in this course, but I've alluded to it from the start, and we might a bit more towards the end of the course, right? Every random variable is a measurable function, is a function of a point omega in the sample space, okay? So the sample space is kind of what the supreme being has chosen for us where we are in the sample space, okay? And that omega will then tell us we're going to get a time which is either 0 or 1 or 2 or 3, anything of these, or infinity, okay? So that's the random variable h of a. I mean, the other book doesn't write it in such a fancy manner. Okay, and then h of a is the infimum n, the minimal time, such that xn of omega, again, the omega is a point in the sample space that actually draws the trajectory of the Markov chain. Okay, that would be for one omega, and this is a point for a different omega, etc., such that xn of omega is in a. Okay, so it's the first hitting time of a set A. Now that set A can be a singleton, okay? It can be a singleton, but it can also have more than a singleton. So this is kind of slightly more general. And here they've also started the time with 0, and they also say that the infimum of the empty set, because maybe this thing, maybe the set here is an empty set because you're never going to hit A, and then you say the infimum is infinite, okay? So then the analogy to SP1 should be clear. So this is, you know, here we asked what is the probability of hitting it in some finite time, whereas infinity means we never hit it. Okay. All right, and I'll get back to MC1 1.3 later. Maybe we won't have time for it today, but I just wanted you to see that this is how they define here. So the H is the analogy of the T. Okay. All right, back to SP1. So what does SP1 have to tell us? Well, first of all, they say that T, this thing, this hitting time or this first return time, if we'd want to call it that, is a stopping time. Now, this is a big concept. This is a big concept where, especially those of you that do finance will see stopping times also later on. Okay, and once we learn a bit of measure theory, depending on how much we'll get to do that, then you can say a bit more about, you know, what stopping times actually means. It means that just saying it now, so you have it. So it's a random variable that's measurable with respect to the increasing sequence of sigma algebras up to that time. Okay, so that's kind of what a stopping time is. But roughly, what we mean is that the event of this time equaling something only depends on, I kind of covered it up here, only depends on what you saw up to that time. Okay, it's often important, it's often relevant, so it's something that only depends on the past. But some things don't only depend on the past. Sometimes the future also matters. Okay, and those things are not stopping time. Okay, and we'll soon see here the strong Markov property, which is related to stopping times. Okay. Now, that stopping time is, or the random variable specific, so T is any random variable. The random variable with the stopping time only depends on the past of the Markov chain. Okay. Now, the event that Ty was n, that you actually hit state y and n, is equivalent to the fact that you were in some not in y in the first time, you're not in y in the second time, not in y in the n minus first time, until you are finally yes in y. Okay, and that's why it is a stopping time. Now, once we believe that this thing is a stopping time, we can invoke something called the strong Markov property. In general, we need to see it. All right? So now, before I speak about the strong Markov property, again, I put you, this is just guide for the reading. It's actually in MC1, it's even going to be a follow-up section. So the same type of proof that we're going to see now for the strong Markov property, we're going to see here in section 1.4 in MC1, the strong Markov property. Okay, written in a slightly different way. Okay, that's a strong Markov property. So what does a strong Markov property tell us? It tells us something that maybe on a first course we wouldn't have even thought that it needs to be a theorem, because it would just seem obvious to us, because it's kind of just like the Markov property, but it's just slightly different. So let's see. All right. So if you have a stopping time, and that stopping time doesn't have to be the specific hitting time, it can be any random variable that is a stopping time. So it's any random variable that only depends on the past. So given that your stopping time equals n, some value n, okay, and x of t at that time t is y, okay, so this is not an x at a specific known deterministic time. This is x at the random time t. Then all the information that you have about the trajectory up to x of t is irrelevant for predicting the future. Okay, so basically the chain after x of t just behaves like a chain from the initial state, and it's kind of something you'd expect. Okay, so basically with stopping times you can reset the Markov chain. We've already reset the Markov chain when we did first step analysis and looked at the probability of transition from one state to another. But here we're resetting the Markov chain at some random time, okay? And that's why this thing is called the strong Markov property, not just Markov property. Okay, so why is this true? And here's a non-measure theoretic proof. The key in this proof, I won't discuss it, but unless ask me questions maybe next time if you have questions about it, for those of you that have read it, or ask me now too if somebody's fully read it, but preferably next time. Okay, so the key is to denote this rather fluid set. Vn is a set of vectors x0 up to xn, so it's a set of possible states such that if you are in these states, then t equals n. Okay, so the event stopping time equals n, you can get to stopping time equals n in a whole bunch of ways. Okay, and once you do that, then there's not more than just a bit of conditional probability. Okay, so the thing is that you look at this joint probability of these three things, and then you sum it up for all the elements here on all the possible ways that you can reach t of n. Okay, so this is equivalent to that. Okay. Well, so sorry. These two elements are equivalent. Okay, so you kind of sum up all the possible paths, that would reach you to stop at exactly time n, and you do a bit of conditional probability in your time. All right, and move on. So we're 26 minutes into the class. This is typically kind of the best time for a joke. Now, I didn't come with jokes pre-prepared today. Here, you don't even need to kind of bravely say them. You can just type them. Anybody want to type something? Maybe you weren't prepared either. No. All right. We move on. All right. So then we have ty. So ty1 is just what we call ty. Okay. That's the first time we hit state y. Okay. From time 1 onwards in this notion. And then tyyk is the case time that we hit state 1. Okay, so it's defined recursively in terms of tyk minus 1. Okay, so it's a kth return time to state y. Okay, so you can think you have a state, right? You're going to return to the first time, second time, third time, etc. Okay, so just imagine that you had now a trajectory of the states. This is state 1, state 2, state 3, and if the trajectory goes, say, like this, okay, so T1 is this one, and that would be time 1. And sorry, not clear, whatever. Let me make it a bit bigger. Erase this. Oh no, better. Okay, so we started here, state 1. So T11, let's call this, would just be 1, okay, because this is time 1. Okay, now next time we're in state 1, I see is here. So let's see, that was 2, 3, 4, 5, 6, 7, 8. Okay, so T12 was 8. T12, get it? T12 is 8. So it's the second return time is time 8, etc. So this is an increasing sequence of times. Okay. Now the question is, are we going to return to a state forever? And then it's going to be called recurrent. Or are we going to not? Okay. So, and that's kind of the difference, the different thing between two states. And we're taking here a different approach than the one where we did an MC1 initially. So I'll go to what I started with today. So in MC1, we just looked at the graphical structure of the chain first. And we could kind of reason, we could say, oh, okay, these states, we're not going to return for them forever because there's positive escape probability out of them. Okay, you can't go back. And same with this state, because there's like, even though you can come in, you know, you can go out, because once you're here, you're never going to be in the yellow or the orange states. Okay, once you're in state 5, 6, you're never going to be in state 4 and 1, 2, 3, 4. Whereas here, we're going to answer this in a different way. We'll say, okay, well, let's write the probability of returning for the kth time in finite time, okay, from state y, okay? So it's starting in state y, reaching state y, k times. What's the probability that that actually happens? This less than infinity actually means that time actually happens. Because if it's infinity, it doesn't happen. So by the strong Markov property, just by iterating the Markov chain in the same way that we did previously, we can just see that that's going to be rho y to the power k. Now, rho y is a probability. When you take a probability to the power k, it's very clear what happens. You get to 0, okay? The only way that's not going to happen is if rho y equals 1, okay? So this thing, as k goes to infinity, can go either to 0 or to 1, right? Because rho y here is fixed. It's some property of the Markov chain, which is the return probability from state y to state y in a single step. Okay. And here we reach those two possibilities and they become evident. So if indeed rho y is less than 1, and that's going to be this case, okay, then the probability converges to 0, okay? And then the state's going to be transient. So we're going to be, it's like, you know, here we might be here in state 1, we might be again in state 1, maybe we'll be again, but after a while, that's it. We're never going to be again in state 1, okay? It's kind of like life. You do, and then something like, for me, what was it? Skiing. I think my skiing. You know, yeah, I did skiing maybe 10 years ago. Last time, might be the last time. I don't know if it's ever going to happen again. And I live with it. So, you know, it's only did it about 6-7 times. Right, transient. However, if rho y equals 1, then the state is called recurrent. Okay, so you return to it with certainty, right? So that's at least its notation so far in its properties. Questions, thoughts? All right, so we go back to our favorite gambler's ruin, even favorite with 4 states, okay? And here there's a bit of analysis that I'll gloss over, and it's a way of actually knowing if a state is transient or recurrent by kind of bounding path, okay? So in the case of gambler's ruin and other chains, it's pretty doable, okay? So here's a type of argumentation. So we're looking at, for example, the probability of, so gambler's ruin, okay? Remember gambler's ruin, you got 1, 2, 3, 4, 0, okay? And these 2 states, I'll draw them. These are the ones where you kind of get stuck on, because there's only an arrow going here and there's only an arrow going here, but these guys have arrows all in between. That's it, okay? Yeah, you only got a 1 and a 1. That's this thing. That's a gambler's run. All right. So the probability of starting in state 1 and hitting state 1 and never hitting state 1 again, okay, there are different ways for this to happen. One such way is that you do an immediate transition from 1 to 0. And that's why you have here the inequality, because it's this inequality, because it's one such way, okay? So I've taken all of the possible path that would yield T1 equaling infinity, meaning never reaching state 1 again, okay? One such path is T1 equaling 0, and that's 0.6, okay? So this is rho 1, 1. So rho 1, 1 equals 0.6, it's greater than 0, okay? And let's look here at rho 2, 2. Okay, here is one way of starting in state 2 and never reaching state 2 again, and that way would be to take, say, the path, this one, that's going from 2 to 1, and then this one, going from 1 to 0. Okay, and if you multiply out these probabilities, it's going to be 0.36, okay? 0.06 squared. All right? And that's also positive. And similarly, or here we just chose a different path, you can look at rho 3, 3, and that's, in this case, we might as well just take this path here. Okay, this path here. And that's with probability 0.4. Okay, so we actually know that rho 1, 1, rho 2, 2, and rho 3, 3 are all strictly positive. Okay, but what we wanted was actually to see if the states are equal, if the rho yy was equal to 1 or different from 1. Okay, so then what is done here is yeah, I mean, so far this is just all we've gotten. Here's another example: social mobility. So this chain, I look at it and immediately see that you can get from any state to any state. Okay, so the argumentation here is kind of a bit is not as straightforward. So what you see is that you begin with, no matter where you start, there's a probability of at least 0.1 of hitting state 3. Okay, so no matter where you start, the minimum of this is 0.1, right? This is hitting state 3. Okay, and hence the probability of this, of T3 being greater than n, so actually reaching state 3 in more than n times, is bounded below by the complement of that, by 1 minus 0.1, which is 0.9 to the power n. Let's see, I have a question here. Doesn't rho 1, 1 equals probability of, Nicholas says, doesn't rho 1, 1 equals a probability of 1 of T1 less than infinity, another one probability T1? Nicholas, you're worth $1 million. Thanks a lot. Good job. Okay, thanks for catching me, Nicholas. Okay, so Nicholas has just shown me that this is not row 1, 1, but 1 minus. Sorry, I was on a trend and actually saying wrong things. Thanks a lot, Nicholas. So Nicholas' comment is, doesn't row 1, 1 is the probability of starting in state 1 and T1 being less than infinity. Okay, so actually being less than infinity. Here we're looking at the probability of equaling infinity. What's the complement of this event? So 1 minus row 1, 1 is a probability of T1 equaling infinity. Okay, well done. All right, so this is 1 minus row 1, 1, and hence row 1, 1, in this case, what we see here is that row 1, 1 is greater, so we see that minus, so this, okay, let's take this. So 1 minus row 1, 1 is greater than 0. So 1 is less than row 1, 1. Okay, right. So we actually see that the state is transient. Very good. Thank you. Clear the mistake? So that implies that state 1 is transient, state 2 is transient, state 3 is transient. Otherwise, having that this is just greater than 0 doesn't give us much sense. Okay, so just to fix this mistake, so what we learned from this is row 1, 1 is less than 1, row 2, 2 is less than 1, row 3, 3 is less than 1. Thank you. Okay, all right, good. Thanks, Nicholas. All right, so here what we're doing is we're doing the similar type of thing. We're taking the probability of T3 greater than n, and we're saying, well, an upper bound for that is 0.9 to the n, and that goes to 0 as n goes to infinity. So we're going to return to 3 with probability 1, okay? So in this case, we do see that the state is recurrent. Okay, now this lemma, which I've never used before, but it's good to have, why not? So it's a way of kind of generalizing all these types of exercises, okay? All these types that have happened above, okay? This is kind of a slightly obscure thing. So we're saying, if we're now starting at state X, okay? The probability, and we can say that the probability of hitting state Y is less than K and it's bounded above by alpha, then the probability of hitting Y greater than NK is bounded by this. Okay. And you could see that the above examples are all cases of this lemma 1, 3. All right. I'll move on to the now SB1 defines communication, okay? And again, this communicating here, remember these are the exclamation marks I started with. So this communication here is X, the way they write is X arrow Y, but it actually means that you can reach Y with positive probability if you go from X, okay? Yeah, that's what we mean by X leading to Y. And then we have two properties. Okay, so the first one is something that was just written as one line in MC1 here. Okay, just keep in mind the difference again. In MC1, they say lead to, where they call communication is the double arrow, and that is the equivalent relation. Okay, and in SP1, they call communication is the arrow. All right, but this is its transitivity property. So let's see this transitivity property in SP1. So if you can get from X to Y, and if you can get from Y to Z, then you can get from X to Z. There is some positive probability, okay? And the way this is done is by saying that, by looking at the Chapman-Kolmogorov equations, okay? So here, this is Chapman-Kolmogorov, which appeared earlier. Okay, so the Chapman-Kolmogorov, I'll remind you, was Pm plus n. Let me write it like this, right? yeah, okay, I'll write it like this. Pm plus n xz is P, well, I mean, you can write it as the matrix P to the power m times the matrix P to the power n, and then we take the xz element of that, okay? So Chapman-Kolmogorov said, let's take all possible paths from x to z, break them in the middle in state after m times, and then do n more steps, and that would be from n to z. Now, one possible path is through state y, okay? So since this is equal, if you just take one possible path from this equation, you get a less than or equal, okay? And that's how you get this lemma. And then comes this theorem, which is if you can get from x to y in positive probability, but there is not certainty that you'll return from y to x, then x is transient, okay? Let's read the statement. So you've got x, you've got y. There's a chance of going to x to y, but you know, this is greater than 0, okay, possible. But this y to x is less than 1. You won't return to x surely. Then, you know, what can you do? After a while, you'll, or there's a chance that you'll never return to x. Then x is transient. Okay, that's at least the meaning of this. Questions about that? All right. And let's move on to the next lemma. So if x is recurrent, so if a state is recurrent and rho xy is positive, then rho yx is 1. So let's see what that means. So you've got a state x that is recurrent, okay? And you've got from y, you're going here with probability 1, okay? This is not an arrow with probability 1. This is, I should do like a squiggly arrow. That means you're going through a whole lot of states, okay? And eventually reaching 1, eventually reaching x with certainty. And you've got here a positive probability, again, a squiggly arrow, a positive probability of being here. Okay, so if x is recurrent in this, then, sorry, if this state is recurrent and you've got some chance of going here, then you must be able to go back, because otherwise it would be a contradiction, okay? So if x is recurrent, if x is a state you're going to visit again and again, and you have a positive chance of going to y, if this was a chance that was less than 1, okay, if it was less than 1, then x would not be recurrent. That's that claim. All right. Then this book describes a 7-state chain, which again, you can do. This is kind of analogous to the MC1 example, and we can see, well, states are, you know, you've got these states where there's communication. I'll use, you know, communication in the MC1 notion. 1 communicates with 5, okay? Or 1 leads to 5 and 5 leads to 1. You've got full communication here, but these two states here are transient. So we've got 2 recurrent classes and 2 transient classes. This is a transient class. A transient class is the recurrent class or recurrent class. Okay. So it's just an example that does that. And we call a set, so this book calls a set of states irreducible if whenever whenever you go out of it, you can go back in. Okay. So set B is called reducible whenever I, J is in B, I communicates with J. Okay. And now people often use a phrase not irreducible for, this is kind of specific for this book, but we say a Markov chain is irreducible, and would mean by that they will have 1 communicating class. Like this Markov chain, I look at it and it immediately see that it's irreducible. Okay. This Markov chain is irreducible. There's one communicating class, whereas this Markov chain is not irreducible. This doesn't contradict this definition, because here, this set of states is not irreducible. This set of states is not irreducible, but this set of states is irreducible. And also this set of states is irreducible, and this set of states is irreducible. Okay. Okay, so if C is a finite and oh, sorry, I made a mistake. This set of states, according to this singleton of states is not irreducible, and this is not irreducible. Only this set of states is irreducible, and this set of states is irreducible. And then we come to the fact that if C is a finite closed irreducible set, then all the states in C are recurrent. Okay, so everything we've been doing here so far has been finite. Okay. So if we have an irreducible set, the close you actually don't need to worry about. So that actually comes from kind of if you had some topology on the states, which doesn't hold. So it's just, if C is finite and it's an irreducible states set, then all the states are recurrent. And this theorem here describes what we sometimes call the canonical decomposition. So let me actually show you this in a new page here. I have a white page. Is this a bug? I don't know what happened here. Okay, I'll just write here. So the point is if you give me a transition probability matrix, okay, and I'll finish soon. So you got states 1, 2, 3, up to n. 1, 2, 3, up to n. So this transition probability matrix has a whole bunch of probabilities, etc. Okay. After breaking it according to this theorem, which says, so transition probability matrix, we're speaking about finite state space. Okay. So what we're going to write is S to be the disjoint union of transient states and some K, whatever they are, recurrent classes. Okay. So what I can do is I can then reorder the states. Okay. I can reorder the states where I'm going to have a block here of states with positive probability and a block of states with positive probability up to here with a block of states of positive probability. So this one is going to be the recurrent class R1. This is a recurrent class R2. This is a recurrent class RK. Then I've renumbered the states. So for this I needed a reshuffle. I needed to apply some permutation, some good permutation on the rows and on the columns of here, right? So by relabeling the states, I need to kind of shift both rows and columns. So then this, you see, this might be like 1 and 2, 2 states here in this recurrent class. So basically what I mean here is that these 2 states are just a recurrent class. And these are, say, 3, 4, 5. That's say in this one, okay? So that's 3, 4, 5. Okay, so that's 3, 4, 5. So these guys kind of live in their recurrent classes, okay? So the row YY for each of the elements in these classes equals 1. You return with probability 1. But then at the bottom here, what I have are the states, maybe they're 27, 28, 29, okay? So these ones are states where I can, I could still have, I have zeros here, okay? Everything else is zeros, 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 zeros. But here is non-zeros, potentially non-zeros, okay? So look what happens with 27, 28, 29. I'm going to put them here. It's very messy, my drawing today. I'm sorry. This is state 27, 28, 29. Those 3 states, okay? 27, 28, 29. So from 27, 28, 29, maybe I can move from 27 to 28, from 28 to 29, from 29 to 27. I can move like that, right? I can move, sorry, these are these movements here, from 27, 28, 29 to 27, 28, 29. Okay, this is a 29 state Markov chain. But there's also some probability here of actually moving and hitting those recurrent classes, right? I can hit this one, I can hit this one, I can hit this one. These are these probabilities here. So these are the transient states. So it's not written in this book, but it's important you know it. So from a matrix form, you can get, if I give you a stochastic matrix, you can reorder it in canonical form and have the recurrent states here as blocks, everywhere else is zeros, and then the transient states. Okay, so that's in a sense implied by this theorem. Now this theorem actually gives an algorithm to actually how to do that, but it's in the proof, and it's not so important. I mean, it's finding a connected component, so that's it. All right, so we're pretty much done with time. Are there any questions before we depart and meet Friday? I think I was a bit messy today, and thanks, Nicholas, for catching that critical error there. What I suggest is, with your time, so you're going to have the project coming up very soon, and then it'll give you this project is here, the what you have here, that's activity 5, right? So you're building up to that by reading these things and doing a few of the exercises. So continue through activity 2, and we'll almost certainly push to finish that on Friday, and then next week we'll be doing activity 3. Okay, so I was asked, is there like a timeline for the activities? Well, the timeline is that this project, project 1 is activity 5, and that's due towards the end of this month, of the months that's starting with us tomorrow, April 1st. No joke. Okay, no questions, thoughts? Okay, Nicholas, on page 17, could you explain how the equation is true? Yes, let's do that. That's an SP1, is it, Nicholas? I assume it is. Yeah. Page 17. Which equation are you speaking about? It must be this equation. Is it? Yes, okay. All right, so let's read the proof of this and see how this holds. All right, so theorem 1.5 says, if rho xy is greater than 1, so if you have chance of getting from x to y, but it's not certain that you'll get from y back to x, then x must be transient. Okay, again, if you have a chance from getting to x to y, but it's not certain that you'll get from y back to x, and x is transient, kind of like international travel these days, right? So let k be the minimum k such that you actually can go from x to y. Okay, so this k is like, I mean, maybe you can't go from x to y in a single step, but there should be some minimal k where you can get from x to y, and that's kind of the smallest possible number of steps that you can get from x to y. Okay, it doesn't mean the mean number of steps or something like that. It's the smallest possible number of steps. It's the shortest path on the graph from x to y. That's what it is. Okay, it's really the shortest path on the graph. So since this thing is positive, okay, and now this thing is positive because rho xy is positive, there must be a sequence y1 up to yk minus 1 such that you can do this. Okay, so there must be a sequence where you go x, you go to state y1, you go to state y2, you go to state y3, you go to state yk minus 1, and you go to y. Okay, that's like the shortest path on the graph. It's not the most probable path, it's the shortest path, okay? Because all it wanted is that for this to be positive, okay? It's not the most probable path. So, and this path is of length k, okay? It has k steps. Since k is minimal, all the yi are not equal to x. Sorry, this is x. Okay, so all right, so none of these are again x. I mean, there's no way that this would be state x here because that, if this was state X, then, it'd be a shorter path just to restart again from X. I mean, if you're looking for the quickest path, shortest path from X to Y in this graph, then, you're not going to go back to X. So all the Y's are not equal to X, so there would be a shorter path. Okay, that's what they say. And then we have, so let's see, that's the probability of starting in state X, X being infinity, being lower bounded by this. So let's see what this means. So this is probability in starting in state X and never returning to state X. Okay, that's what it is. Probability in starting in state X and never returning to state X. So there are all kinds of ways of not returning to state X. Okay, but one way is doing this path X, Y1, Y1, Y2, Y ta 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 up to K. So going through this path, okay, up to Y, and then not returning. That's 1 minus rho YX. So rho YX is the probability of returning, and this is not returning. Okay, so there's all kinds of ways that this event Tx equals to infinity will hold, and this is one specific way. Okay. And this thing is, so the reason that the author chose to write the shortest path is that it's just that this is kind of a concrete, well-defined path. This is kind of a path of length k. Okay, this is some path of length k that doesn't involve x in the middle. Okay, so this is a path of length k, and this thing is rho yx less than 1 is a precondition of the statement. Okay, so if rho yx is less than 1, then 1 minus rho yx is greater than 0. Okay, so then this thing is greater than 0. So this is greater than 0, this is greater than 0, so this is greater than 0. So then you actually have a positive probability of not returning to state X, and that's why the state is transient. So that's a proof. Did that answer, Nicholas? Okay. Other last minute things? Don't have to be last minute. Can be minute before last things. No? Okay. I'm sweating here like a hog. It's just been very hot in this room because closed doors. Stay positive. If anybody's under some stress of any sorts, this is a bit of a rocky period. Don't hesitate to drop me a line. And you'll hear from me about the project, and see you Friday and in Piazza as well. Bye, everybody. Now, I hope this recording is going to work. Let's see. Let's see. Amin? Yep. Bye-bye. All right. Ciao. Okay. I'm leaving it.